Hello and welcome to the lesson on forces in two dimensions and surfaces at an incline. So our goal today, I can apply Newton's three laws in two dimensions for real world situations, and that includes surfaces on an incline. So let's talk about what a frictional force is, or a bit of a review here. So a frictional force occurs, when two bodies slide over each other. So these forces are sometimes welcomed. So the ability to stop. If we didn't have friction, we would not be able to stop, wouldn't be able to move. And sometimes it's a hindrance. So obviously being dragged across shag carpet by your friends, getting carpet burn, not a positive thing. Sometimes any scrapes or bruises on asphalt, obviously friction, not a positive thing there as well. So there's the good and the bad, and it depends on the application and what we want. So let's take a microscopic look here for a second. So in terms of what a frictional force looks like, I'm just going to take one object sitting on another, so basically a box on a table, if you want to think of it that way. And what we're going to do is we're going to zoom in. We're going to zoom in on this region, and if we zoom right in, we see that the tabletop, so I'll do that in black again, the tabletop, when you zoom in, there'll be small imperfections in the surface. Similarly, the bottom of the box, which I'm going to do in green, also has similar imperfections. So I've got the box interface, oops, wrong way around here, table, flip my world for a second, table, and the green is the box. So if you were to rub them back and forth, so if we move these back and forth against each other, we have imperfections in that surface. So we've got imperfections on the surface. So those imperfections, that's what leads or causes that friction. So imperfections on the surface cause friction. All right, so it's like you have two toothed objects, you're going to get stuck, you're going to be caught in certain regions. So with that jagged edge, if you get two teeth grabbing together, you have to increase the amount of force to pull it over. That interaction creates kind of a grinding, and this is where you get your heat. It's like rubbing your hands together. If you don't press your hands together very tight and rub them together, they warm up. If you really press on them together really hard and then rub them back and forth, the imperfections in your skin, because they're rubbing and grating against each other, creates that heat from that frictional interaction. So it's those imperfections that are our main problem when it comes to friction. So looking at the grade 11 course, so force of friction always acts opposite to the motion of an object. So the force of friction depends on the applied force perpendicular to the surface. We talked about that last year. That is your normal force. And we said the normal force is very, very important. So the normal force, F of n, that'll be a vector, so we need the vector notation. The equation that governs it, we talked about this in the grade 11 course, is that your force of friction is equal to mu, your coefficient of friction, multiplied by the normal force. In grade 11, I made a big deal talking about that normal force. That the normal force, and I'll put it underneath here, that force due to friction is equal to coefficient of static friction, and it's the normal force plus or minus the applied force in the y. So you remember that. So again, that is still key for us in the grade 12 course. So please make sure you box that up for your formula for force due to friction. All right, so mu is the coefficient of coefficient of friction, and there are two types of friction. So talking about normal force here, static friction is the first type. The greater of the two forces, okay, static friction, it works against a stationary object. So we're looking at static friction, dealing with stationary objects, and that we're just trying to get them to move. So it's a lot tougher to move something that's not moving than it is for an object already in motion. So if we take it back to that microscopic analogy here, once you get something in motion, then that interaction between the two surfaces, it's already in motion, it's kind of sliding over, it's like a car. Okay, once you get it in motion, it's a lot easier. You got a little bit of momentum, and the velocity, you find that maybe those grooves aren't going all the way down, all right, or gripping completely. Kinetic friction, then, that is the force that opposes motion of an object already in motion. All right, so whatever you're pushing or trying to move, it is already in motion. Okay, moving along. So an example. You attempt to move a large beverage fridge with a mass of 250 kilograms in the clubhouse. You have to apply a net force of 400 to start the fridge moving, and then nearly 280 to keep it moving. So answer the following. So free body diagram, even before I get into A, we are in the dynamics and forces unit. So I'm going to push on this fridge, and my F net, so, or unbalanced, I guess you'd say, for situation is 400 newtons, and I'm pushing it to the right. So this is for part A. Part B, my F net will change. So it drops down to 280 newtons. That's for part B. What else is acting on our particular fridge? Well, we do have a force due to friction. We have our force due to gravity. And we'll have our normal force. Oops, that would be force of friction, which is not in the vertical direction, so normal force. Excuse me. So there is our diagram for both questions A and B. So question A, calculate the coefficient of static friction. So at this point, we're just decoding. So we want to know what mu is, and we want to know mu subscript s for static. We know that force due to friction is equal to mu static multiplied by our normal force. Each of these particular values have an associated equation. So our force due to friction, we know that, and I'll put this over here maybe, our force due to friction has to be, if we're going to get it moving, the minimum amount is a little bit bigger than 400. Okay, so if we assume 400, it's going to be our minimal amount. It really should be greater than or equal to 400 to get it started. It should be greater than 400. So how about we do this? Force due to friction is greater than 400. We're going to assume 400 for the minimum. Assume 400 newtons for minimum. Because if you go 400.0001, this fridge is going to move. So that being said, substituting my 400 here, mu s, normal force, is mass of the fridge multiplied by gravity. So 400 equals mu s. Mass of this fridge is 250. And again, for this course, I'm just going to use gravity as 10. Makes the math a lot easier for myself. So we end up with our mu s being equal to 400 over 2500, which we're going to call equal to 0.16. So therefore, static coefficient of friction is 0.16, which is relatively low, so it must be on a fairly smooth surface, so maybe a hardwood floor, for example. Now we want to calculate kinetic friction. So it's the same idea with the kinetic friction. We're going to make an assumption here. So I'll do B part under here. We're looking for mu k. So what does that look like? Well, in order to keep this fridge going, we have to have an F net of 280. So our force due to friction, in this case, the forces will be balanced. So we can actually say 280 newtons. All right. So our force due to friction has to equal at least the applied force there in order to go ahead and solve this particular question. So we return to the same formula once again. Force due to friction equals mu k multiplied by normal force. So 280 is equal to mu k multiplied by mass, still 250, gravity still 10. So now we have 280 over 2500, and 280 divided by the 2500 gives us 0.11. I guess I'll throw the 2 on there for good measure. So it is a little bit lower. So static friction and kinetic friction are fairly close together. So it must be a fairly smooth surface. Like I said, like a hardwood or something along those lines. So our mu K is 0.112. All right, so there we are. Next slide, I guess. So now we're going to look at Newton's law in 2 dimensions. And we're going to kind of combine this with some of the stuff we already talked about. So Matt drags Tristan through the snow by his ankles. We know Tristan has a mass of 65 kilograms. And while being dragged, his legs make an angle of 50 degrees with the ground. So basically what's happening, we have someone that's being dragged through the snow by another individual. All right, and we know the angle is 50 degrees. So we're going to simplify this with a point diagram using our FBD. So we're going to draw a free body diagram. So we know the mass of our object is 65 kilograms. The legs make an angle of 50 degrees. So that means that whoever's pulling here is pulling the person at an angle of elevation of the 50 degrees. We know that the force applied here is 200 newtons, so that's how hard Matt is pulling this individual. Coefficient of friction is 0.3, and we want to find acceleration. So what is the acceleration of this poor person that's being dragged along? So finishing up the free body diagram, what's involved here? Well, we have our force due to gravity, we have our normal force, and we'll have our frictional force. And remember, from our vectors, we are going to have FAX, and we will have FAY. All right, so that 200 gets broken into its 2 components, FAX plus FAY. So this is from grade 11, and it's from earlier in this unit when we talked about the vectors. So what are we looking for? We want to find acceleration. Acceleration comes from FU ma. All right, so we're looking for A. We know the mass. All right, and you can do this in steps. I'm going to do it all together in one. So we need to find this unbalanced force. Again, balanced force comes from FAX minus force due to friction equals mass times acceleration. So unbalanced force comes from the difference between the two. FAX, from your vectors, magnitude of the force, cos of the angle. So there is my FAX. Force due to friction is, maybe I will take that back a step. So you can leave it if you've already written it, but it's magnitude of force, cos theta, minus kinetic friction, mass times your gravity. So here's an example where the normal force is actually mu Fn equals mass times acceleration. So the normal force, we got to talk about that for a second. So it's going to be 200 cos 50 minus mu. Now, the normal force is going to be reduced because your force due to gravity is in the opposite direction of FAY and your normal force. So that means that the normal force is not going to just equal gravity. So now I'm looking over here. Okay. If I take that formula there, or take that, we know that force due to gravity is equal to FAY plus your normal force. So if I want to find my normal force, rearranging, normal force is equal to force due to gravity. In this case, we're going to have to subtract FAY. So it's actually reduced our normal force. So I'll just group that together here and shrink that down like that. And I'll finish this in the next video.